Well, welcome back. It looks like it's just you and me, Caitlin. You're going to get a private chapter, 14 lecture. All right.
Sounds good.
All right. Any questions before I start? Do you have any questions about anything in general?
No, I'm good.
Okay. Sounds good. I'm sure some other people will join in here. They were probably running late, but well, I am recording it so I can upload it for the ones that couldn't make it. So anyway, what I have planned, I should say, is today's the 19th. So I hope to do chapter 14. It may go over to next Tuesday, maybe. We'll see. It's fairly long. Okay, we got one more. So we'll see how it goes. So if I find it, I need to go over. I might make it for, let me take a look at 15, see what I estimate. I'll send an email out either way. Okay, we got one more. Let me let them in. Okay, welcome back, everybody. All right, so what I'm going to do is, unless there's a question, any questions from anyone? Dina, Clarissa, any questions? If not, I will jump into chapter 14. As I was telling Caitlin, I may carry it over to next Tuesday. We'll see how it goes, okay? But basically, we have this chapter. Next Tuesday is chapter 15, and then the final is the following week. So, you know, it's coming to the end here. Okay, got one more. Let me go, let me admit them. Okay, well, chapter 14 kind of puts it all together little by little. We talked about the elements, as I mentioned before, and we got into compounds and different reactions and so forth. And this is an additional part about chemistry, which is called intermolecular forces, I-N-T-E-R, as compared to the term intra, okay? A big difference. So when we talk about inter, I-N-T-E-R, versus intra, we are talking about totally different forces. Intermolecular forces, I-N-T-E-R, are forces that occur with other molecules or with each other, be it the same molecule or even other molecules that are different, okay? And that is related to the polarity of the compound. So remember, we talked about polar bonds, okay? And from polar bonds, we went on to determine polar molecules based on their geometry. Okay, so it's kind of a refresher. You must, if you need it, go back to figure out, well, how do we determine what's polar and what's non-polar? Because what we're dealing with is on the outside of this molecule are electrons, okay? And how they interact with other molecules is a big factor depending on whether it's a polar molecule or a non-polar molecule. Now, with respect to intra, I-N-T-R-A forces, those are the forces that keep a compound together. Those are basically the bonds. What type of bond? Well, we have two types of bonds, right? We had the ionic bond and we had the covalent bond, of which the covalent bond, we had two subsets, the polar bond and the non-polar bond, okay? And so we're going to talk about that because these intermolecular forces have a big effect on the properties of molecules, such that the boiling point of a molecule is dependent on the intermolecular forces of that molecule. And some of these forces are pretty strong. And that is why some molecules, when they boil such a high temperature. For example, water. Water boils at 100 degrees Celsius, fairly high temperature, okay? as compared to, let's say, something that's volatile. A good example would be fingernail polish remover. I'm sure we've all encountered it someplace somewhere. You take the cap off and you can just smell it. It's very volatile. It evaporates very quickly. And that is because those intermolecular forces for the nail polish remover are much weaker than the intermolecular forces of those molecules that have stronger ones. And what's happening is these interactions between molecules, the strength of these, let me move on to the next slide, maybe explain a little bit better, okay, graphically. And so what we're looking at here is if we look at these two molecules, for example, there's two diatomic molecules, and we look here at this dotted line, that dotted line represents this interaction between molecules. And those are the intermolecular forces. If these forces are very strong, it takes a lot of energy to break those forces up. Hence, if they're strong, it could have that could result in having something like what we call high boiling point. That is the temperature that compound would boil. Okay, water, for example, as I stated, boils at 100 degrees, and acetone much less. So, not to confuse the two between the intermolecular forces and the intramolecular forces. Those forces are what hold the molecules together, the atoms together, the bond, the chemical bond, either ionic bond or a covalent bond, okay? So we need to review polar bonds, okay, and non-polar bonds, because that's gonna tell us what type of intermolecular forces we're dealing with, of which there's only 4 types, only 4 types of forces that we're gonna work with. And how we assign which force to a molecule depends on the polarity of the molecule. And so go back and refresh your memory. Remember I stated that when we're talking about covalent bonds, whenever we have, let's say, a species of, hold on one second, let me get my wrong pen here. If I have a bond between, let's say, A and A, where the atoms are the same, that bond between them, defined here by that hyphen, that line, is an equal share. It's a covalent bond, but it's equally shared because remember the electronegativity? Electronegativity was a measure of the affinity for an atom to pull the electrons onto itself. Okay, it's a measurement. And when something has a high electronegativity, it will tend to pull the electrons onto itself. Okay, in this case with A and A, they're both the same. So the electronegativity is equal. Therefore, we have an equal sharing of that bond, an equal sharing of those electrons in that bond. Now, if we just substitute that A with the letter B, which represents a totally different atom, now we have a differential with respect to electronegativity. We have 2 different atoms, A and B, and results in a dipole. We call the dipole 2 poles. In this case, a partial positive side and a partial negative. Which direction it went to depended on the electronegativity of A versus B. And what that was and how we found that we're using the periodic table, because we know that fluorine is the most electronegative element, okay? So, and the trend was the electronegativity, which is an actual value, increases from left to right across the periodic table, or down to bottom, down to up increases. And all of it points to fluorine. And so we use fluorine as our benchmark. We don't have to memorize every electronegative value for every atom because they do have that. There's 118 electronegative values there, a little bit less, but of the majority of the elements. The radioactive ones are a little bit more difficult to get because they don't last very long. Anyway, we use fluorine as our benchmark, and if we were comparing A and B, and let's say for argument's sake that B was closer to fluorine, that tells you that B is a lot more electronegative, okay? Which meant that I have a dipole, which meant that I have an arrow that goes from left to right, which tells you, I get more information, that you have a partial negative on the B and a partial positive on the A. Partial because it's not a full-fledged positive and negative like ionic compounds. Now we identified that it has a polar bond, okay? From there, we also looked at the geometry of the molecule. Remember Lewis dot structures? Okay, because the Lewis dot structure gave us the geometry of that molecule. And that arrow represents, if you recall, what we call in mathematics is a vector, meaning that that arrow, length of that arrow has magnitude, has value and direction. So this arrow is being pointed from left to right, the way it's written here, okay? Which tells you that you can graphically add and subtract these arrows. So if I have two arrows pointing in the same direction and roughly the same length, meaning the same magnitude, so this might be 1 unit, that might be 1 unit, and since you're going in the same direction, I get a net 2 units of information. If they went in opposite direction with the same magnitude, opposite direction, guess what? They cancel, because when the one on the left is going with a negative value, the one on the right is going with a positive value. The result is they cancel out. And so we did a couple examples of carbon dioxide, if you recall, where we had 2 dipolar bonds, carbon to oxygen, going in opposite direction. And so here we had 2 polar bonds, but because they canceled each other out, we ended up with an overall nonpolar molecule, okay? Another example we had was the tetrahedral. And if we had a tetrahedral configuration, refresh your memory on those configurations, they look like something like this. We have 4 carbon fluoride bonds. We would think that we will have 4 polar bonds, which results in a polar molecule. But because of the geometry of the tetrahedral, and because all 4 bonds are carbon fluoride, they cancel each other out, resulting in a nonpolar molecule, even though it has 4 polar bonds, okay? Now, all this is important here because we're gonna take this information and assign to it what type of IMF it has, okay? And then from that, we're going to be able to do a relative comparison of such physical properties as surface tension, boiling point, viscosity, and vapor pressure. Those 4 physical properties. We'll be able to compare and contrast 2 different molecules and determine which one would you expect to have a higher boiling point based on, 1, their polarity, which then results in assigning an IMF interaction, IM force to it, which then we're able to answer that question, okay? But it's all tied into the polarity of the molecule, and that's what I'm trying to do here to refresh our memory of what we talked about a few chapters back. Now, in this scenario here with the 4 fluoride bonds, if I were to replace one of those bonds with not a fluoride, but anything else, instead of fluoride, maybe I replace it with hydrogen or even another halogen like chloride. Let's just say hydrogen. So now I got 3 polar bonds and 1 carbon-hydrogen bond. Remember, the carbon-hydrogen bond is like this example with the AA, where you have an equal sharing of that bond, so results in a nonpolar bond for AA example. But carbon-hydrogen is another example of anything with a carbon-hydrogen, it is a nonpolar bond. The electronegativity between carbon and hydrogen difference is negligible. They're treated as the same as if you were working with the diatomic molecule. So that would be a nonpolar bond. All right, so the fact here, three polar bonds, 3 carbon fluoride bonds but one carbon hydrogen. The result is that this is not nonpolar anymore, but it is now a polar species. Okay, and once it's a polar species, then I can assign a IMF to it. Okay, so refresh your memory about polarity, polar and nonpolar molecules, and even ionic compounds. What defines an ionic compound? Right. So this is just a rehash of what I just talked about. In this example, we have hydrogen, HCl, okay, which we see as the example of the AB, two different atoms on the molecule, two different atoms, meaning you have a polar bond. The chloride's a lot more electronegative, so we have a dipole going from hydrogen to chloride, giving us a partial negative on the chloride and a partial positive. Now, that is a dipole, okay? It is a permanent dipole. The nature of the beast, because of the difference in electronegativity between these two atoms, it has a permanent dipole, just like a magnet, positive and negative, north and south pole, okay? So we're having a partial positive and a partial negative side. Guess what? It will interact with other molecules because a partial negative will interact with the partial positive of another molecule, resulting in this interaction here, this intermolecular force between hydrochloric, two molecules of hydrochloric acid in this case. And this, is two-dimensionally, but you can think of it in three dimensions because this is occurring in, not only along the X and Y axis, but in the Z axis. So all this interaction is all around all these molecules that are all lined up. Okay, so we could have another one over here. As so on, and just continue on. Okay. All right. Now, there are 4 types of intermolecular forces. These are interactions that occur between the partial positive and the partial negative charges, or charges between molecules. All right, the very first one. This is called the London Dispersion Forces, okay? London Dispersion Forces. Point number 1 about this force. It is, of the 3, there's actually 4 we're going to talk about, but the 3, 1 through 3, we're going to talk about deal with covalent compounds. The 4th one deals with ionic aqueous systems, and we'll have more to say about that in a second. Well, number 1, this is the weakest of the 3 forces, okay? The main criteria to assign this force is that that molecule must be nonpolar. So any nonpolar molecule you have determined to be a nonpolar molecule, the only force that they have, the only intramolecular force they have is the London dispersion forces, which happen to be the weakest, okay? All right, the next force is called a dipole dipole. So as far as strength is concerned, when I compare these 3 that we're going to talk about, this is like medium strength, okay? Now, the criteria for this force is that it must be polar. That molecule must be polar. So now I'm hoping you can pick up a quick trend here. So once I define a molecule that is polar, and we know by its geometry that it is a polar species, then first of all, London forces have no play here. They don't interact. It will be one of these 2, either number 2 or number 3. Okay. Number 3 force, which is the strongest of the 3. So this would be the strongest of the 3 force, okay, is called hydrogen bridging force. Now, it is very similar to the dipole dipole force, okay, very similar with one exception. It only pertains to hydrogen that is bonded to nitrogen or oxygen or fluoride, okay? Now, let me repeat that, okay? Yes, the bond, a hydrogen-nitrogen bond, a hydrogen-oxygen bond, hydrogen-fluoride bond, yes, it is dipole, dipole. It is a dipole bond, okay? However, because of the nature of the beast, between the hydrogen and NOF, as we call it, not on file, nitrogen, oxygen, fluoride, it has an additional strength property about it, okay? And that property is called hydrogen bridging force. Now, the old literature may call this hydrogen bonding. And you'll see that name pop up occasionally. That was the name that it was given to for the longest time. But it's not a true bond, okay? When you talk about hydrogen bonding, it's an interaction. It is an intermolecular force. So they're trying to get away from the term hydrogen bonding and use the term hydrogen bridging force, okay? Just like ionic bonds, and when you think of bonds in general, you think about electrons being shared. And when you talk about ionic bonds, yes, it is true. It's not a true bond because we have a full positive and a full negative coming together and attract to each other. Okay, as compared to covalent bond where we're having an interaction of electrons. Okay. So London dispersion forces, dipole forces, and hydrogen bridging forces. Okay, hydrogen bridging force is much like a dipole. It really is a dipole, but because the nature of the beast, it only pertains to hydrogen bonded to either nitrogen, oxygen, or fluoride. And that is the strongest force of those three, okay? Now, keep in mind, think about this. If that is, we're looking, let's say this dotted line represents the interaction between two molecules that are, interacting with each other in the liquid, okay? Whatever they may be. With London forces being the weakest, it will not take very much energy to break that interaction up, okay? As compared to hydrogen bridging, where it has a little bit stronger amount of energy is required to break up that interaction. Okay, so that's what we're talking about. We're talking about breaking this interaction between molecules in the solution, or most of the time they're in solution, breaking that interaction. Okay, and finally, the last one is called the ion dipole force. Well, point number one, they talk about ions. So most of the time, the majority of the time, says it's an ion, then we're talking about ionic compounds. That's what we're talking about. So those are metal, non-metal compounds. Whether they are totally soluble in water or just insoluble. Remember, even though they're insoluble, they're still a small amount in solution of ionic compounds. And so these are ionic compounds in some solvent which has a dipole, which happens to be water. So normally, 99% of the time, we're dealing with an ionic compound in an aqueous system, which is water, okay? Has nothing to do with the interaction of covalent compounds, which 1, 2, and 3 do, okay? All right. Let's talk about London dispersion forces. These forces are a little bit, they're temporary actually, okay? And there are attractions between nonpolar molecules. Now, what's happening is you got one molecule that has electrons coming close to another molecule has electrons on the surface. And the result is, remember, electrons are negative charge. The electrons of one molecule of a nonpolar species are going to repel the electrons of the other. which results in a temporary dipole, results in a partial negative and a partial positive section. A classic example of this, you can try this at home, you have a balloon, is take a balloon and rub it on your head or someone else's head, okay? Rub it on your head and then take that balloon and then put it on your chest, okay? Or on the wall or someplace. It will stick, okay? Now, it will not stick forever. Eventually, it's going to fall down. Now, you might ask, well, what's going on here? Is this some kind of Harry Potter magical thing going on? No, not at all, okay? What you're doing is you are taking the electrons for one. Point number one, electrons are all around you. Don't believe me? Walk on some carpet and then touch some metal, okay? Or if you're out shopping, some of these carts, sometimes if you're pushing a cart, they build up a static charge and then you transfer the charge to you and then you touch something and you get zapped. All right, so that zapping aspect is those are electrons all around us. So they're all around us, okay? Loosely bonded, but they're all around us. Now, when you take that balloon and rub it on your head, you're transferring some of those electrons onto the surface of the balloon. So you're maximizing the electron concentration on that balloon. As you take that balloon and you put it to your chest or the wall, remember, on the surface, there's electrons. Surface on my chest, there's electrons here, or on the wall. As you bring those negatively charged electrons in the balloon closer to your surface, whatever surface it may be, those electrons on the surface get pushed away because it's negative on negative, right? And the electrons are negative charge, resulting in a partial positive area on your chest or the wall. So you got a full partial negative because of the electron excess you put on the balloon. You created a partial positive area on your chest, and positive attracts negative, and guess what? They stick. That balloon sticks on you for a little bit. Eventually, it dissipates. It's not permanent. If it was, that balloon would be with you all day. But it's not. It's just a temporary because the electrons finally go back to the ground state that's being pushed into an excited state, and everything goes back to, quote, whatever equilibrium they have. So they fall off. So that's an example of a temporary attraction between nonpolar molecules because these electrons are interacting with each other, okay? Most of the time, nonpolar gases, which end up to be, a lot of them are nonpolar, have London dispersion forces. And they're not very close to each other. They don't interact with each other. So those forces are very weak, and hence their London dispersion forces are pretty weak, but they're there nevertheless. Now, within nonpolar molecules, this is the last part, within nonpolar molecules, the bigger the nonpolar molecule, the more electrons, hence the more London force. When we compare nonpolar molecules, so if I have a nonpolar compound, long chain hydrocarbon, okay, maybe 20 carbons, nothing but carbon and hydrogen, all nonpolar, and I got maybe a 2-3 chain carbon chain hydrocarbon, okay, all carbon hydrogen. Well, the longer chain is going to have a lot stronger London forces simply because there's more electrons, okay? More electrons, more areas for interaction compared to the smaller one, okay? So bigger molecules, more electrons, more London forces. This is kind of depicts what I was talking about with the balloon coming in, you rubbing that electron onto your surface. You, in effect, you bring in the balloon with the electron, a lot of these little dots here represent the electrons. Well, that kind of pushes these electrons away from that surface, creating a partial positive area, and then we've got a partial negative. So they kind of stick together for a little bit, okay? And the same is true from the other side. So there is a temporary dipole. Okay, this is a dipole, but it's only temporary. These are for non-polar molecules. Okay. With respect to dipole forces, these pertain to those molecules that have a permanent dipole. Permanent because the molecules, the bond at question is between two different elements, plain and simple. You have two different elements, you have two different electronegativities, you result in a permanent dipole. And so one of them would have a higher electronegativity, so therefore we create a partial negative toward the chloride, and the arrow goes from left to right, okay? So when it sees another molecule of hydrochloric acid, HCl, we get an interaction going on because of the partial positive and the partial negative. All right, so dipole-dipole interaction. There's a dipole here, there's a dipole here, dipole-dipole. Of course, like I mentioned, they're stronger in London forces, and of course, they have to be polar molecules. Now, with respect to hydrogen bridging forces, okay, as I mentioned before, it only pertains, it is a dipole, no question about it. If you look at hydrogen and hydrogen and oxygen, there's a dipole right there, okay, going toward the oxygen. And it's a permanent dipole. And the same is true for the other side, okay? But because it is hydrogen bonded to oxygen or fluoride or nitrogen, and has an additional force, it has a little bit stronger force, and that is called hydrogen bridging force, okay? You can see here that interaction is really no different than a dipole-dipole. It just happens to be a stronger interaction right here, much stronger interaction. Okay. And again, the one on the picture on the right kind of trying to show you a three-dimensional picture of how things probably look, you know, because, you know, chemistry or nature is really a three-dimensional world. We just happen to show you, well, trying to show you two-dimensionally. But do keep in mind that, yes, it's a three-dimensional world. The hydrogen bridging is stronger than dipole-dipole. Yeah, all these forces are still weaker than either the ionic or the covalent bond, okay? Strong as they are, we're not talking about the length and the strength of a actual bond, be it covalent, be it ionic. All right, so the last one, number 4, deals with an ion dipole force. Normally, we're dealing with an aqueous system, okay? Because water, the dipole, we've got ion, which means it's the ionic compound, and the dipole deals with the dipole of water, because water is very, very polar, okay? And we can see here a depiction of a sodium ion that is being hydrated, if you will, for the water molecules is being interacting, the full positive of the sodium ion interacting with the partial negative of the water molecules. Now on the other side, if this was, let's say, sodium chloride, Cl, well, the chloride would be over here interacting with the partial positive of the water molecule. So we have this big old gigantic matrix of sodium ion and chloride ion hydrated by the water molecules, okay? All right, now, when we'll be asked questions to assign what kind of force, the criteria to assign number 4 is this. 1, it must be ionic. An ionic compound must be talked about in the question. If they don't talk about an ionic compound, then number 4 is not something we can assign, okay? Right. Let's just kind of rehash some information that we've dealt with here before. Bonds versus the forces. Bonds. Number one, we have ionic bonds. That's an interaction between a metal and a non-metal ions. Okay. We have covalent bonds, of which we're either polar or non-polar. Okay. Polar bonds, the electrons are unequally shared between the two different non-metal atoms. And nonpolar bonds, that those electrons that are being shared are shared equally. Okay. So with that information, knowing what type of bond we got, that also would tell us what in geometry would tell us what type of molecule. We have geometry, whether it be polar or non-polar. Okay. Remember, the general guideline was this. When we look at the bond, let's talk about covalence, refresh our memory of covalent bonds. We identify a covalent bond. Then from there, we identify it to be either polar or non-polar. Now, if the bonds on that molecule, if all the bonds in the molecule are non-polar, like a hydrocarbon, then you can safely say that that molecule is non-polar due to all the non-polar bonds in that molecule. Okay. Now, with respect to polar covalent bonds, once you identify to have polar covalent bonds, the next question you must ask yourself, are these polar covalent bonds that I've identified, are they canceled? Can they be canceled out by another polar covalent bond? If the answer is no, then you got a polar molecule. If the answer is yes, and the bonds are canceled, like the carbon dioxide example or the tetrahedral example I talked about earlier, then you have a nonpolar species. Okay. Now, once you identify that, now you can identify what force. So, London forces. Once you identified that molecule is a nonpolar species, that's the only force they have, and that is the London dispersion force. Okay. The next question is, well, they're polar. Well, they're polar, they're going to be one of the two, either dipole-dipole or hydrogen bridging. We can eliminate hydrogen bridging if it's only because hydrogen bridging only is related to hydrogen bonded to either nitrogen, oxygen, or fluoride. Okay? And if it's not that example, then it's a dipole-dipole force that we're working with. And then finally, at the last one, the ion dipole force. Well, criteria number one, and we're talking about ions, it has to be an ionic compound, and specifically an aqueous system. Okay, it's like 99.99% of the examples that we're going to deal with. So it's an aqueous, water has to be mentioned, and ionic compounds. All right, so we may have a table as follows. And they might ask the question, okay, first of all, is it polar or non-polar? Okay. Once we identify whether it's polar, excuse me, or non-polar, then we can assign its strongest intermolecular force for that molecule. All right, so which means that you may have to go back and review how you did Lewis-Dot structures, okay? Because remember, from the Lewis-Dot structures, we came up with the general formula of ABE. ABE then tells us, based on the shapes table, the geometry of that molecule. And that geometry of molecule then would tell us, depending on the polar bonds, whether they cancel or not, whether it's polar or non-polar. Okay, so we haven't, dropped the Lewis-Dot structures. We still need to use them if needed. All right, so we know that carbon dioxide is non-polar, and we talked about that because we demonstrated that we ended up with this geometry where we have two polar bonds, but because of the geometry of the molecule, these two polar bonds cancel each other out. Therefore, it is a non-polar species. And being a nonpolar species, the only force they have, intermolecular force, is the London forces. Okay. BF3. If you go through the Lewis dot structure, it'll be very much like ammonia structurally. And you should end up with this type of geometry. Okay, with a lone pair sitting in the central atom. Now, if you recall doing this when we're doing Lewis dot structures, I stated at that time, whenever you finish with a Lewis dot structure and you end up with a lone pair on that central atom, 99.9% of the time, what you have is a polar compound. Okay. Now, we may think that based on the geometry here, that we would have a tetrahedral geometry, but we don't, because we have three polar bonds. And because the lone pair take up a lot of space, those polar bonds are kind of squished in, so they're not really canceling each other out. They're kind of squished in at an angle, resulting in a net polar molecule. Once we identify it as a polar molecule, we can eliminate London dispersion forces because you got to be nonpolar. We can eliminate ion dipole because we're not dealing with any ion compounds here. So the only choice you got left is either dipole or London dispersion forces. It can't be London dispersion forces because that only pertains to hydrogen and nitrogen, oxygen, or fluoride. Well, we have no hydrogen at all. So the only logical choice you have left is the dipole. Okay, so I'm showing you how to go about this systematically, stepwise, and answer those questions, and eventually you end up with the answer that you're looking for, that is required. Here, you have London dispersion, dipole, okay? Next one up, HF. Now, I'm hoping that you can recognize the two things. One, I have hydrogen and I have fluoride. First of all, I got two different elements bonded together. Automatically, it's polar, right? Unless it's, carbon hydrogen, then it's nonpolar, but it's not carbon hydrogen, it's hydrogen fluoride. So we have a polar species here, okay? The fact that we have a polar species only leaves you with two choices. That's either dipole or hydrogen bridging. The fact that we got hydrogen and fluoride involved automatically should send you to the hydrogen bridging force, okay? Yes, it is a dipole, but because it is bonded to hydrogen, the bonding is between the fluoride and hydrogen, it's got a little bit of extra strength due to that relationship. And therefore that extra strength is what we call, or extra property is what we call hydrogen bridging. Okay. All right, number 4, the last one, carbon hydrogen. I hope that you recognize that in this molecule here, the only thing that's associated with it here is carbon hydrogen, nothing else. Okay. Hopefully that should tell you, okay, carbon hydrogen, guess what? I have a nonpolar species, okay? Specifically a tetrahedral shape. You can go through Lewis dot structures and you'll be tetrahedral, but the carbon hydrogen bonds are not dipole bonds, they're not polar bonds, they're nonpolar. So 4 nonpolar bonds, nonpolar species, automatically London dispersion forces. All right, then finally the last one, you see potassium iodide, aqueous potassium iodide that is ionic in polar water, and its force is ion dipole. Now, a word about that ion dipole. Notice, in order for that to be true, we must have an ionic compound, okay? plain and simple. And so this has really nothing to do with the other three forces, London, dipole, hydrogen bridging. Okay, so you can't have dipole, dipole, or hydrogen bridging or London forces in this Ki system. Okay, now with this information, we can extrapolate some physical properties and say that with excluding the last one, that the one with the weakest force would have the lowest boiling point. So these two will have the lowest boiling point. And we can even go the other direction and say, this one, hydrogen bridging, would have the highest boiling point. So HF would have the highest boiling point, and the weakest would be those two, carbon dioxide and methane, because they have the weakest intermolecular force. And so that's what we mean by relative comparison. We can't really do absolute comparisons and say exactly 100%. Yeah, water boils at 100 degrees due to whatever intermolecular force. No, all we can do is a relative comparison between two different molecules. All right. This equation here, I'm not going to say much about this equation, but I'm just going to just say the following. Okay, is this. This Coulomb's law, basically what this is a mathematical equation that relates the strength of interaction between two charges. But I'm pretty confident that you're already familiar with this concept, okay? Because if you take two magnets, for example, and let's say we put them opposite charge because you can really feel the force. So south on south or north on north, if you put them apart, 3 or 4 inches, I don't really feel much repulsion, right? But as I bring them in closer, you can really feel that force really kick in until such time that I bring them in just about touching, and that force is fairly strong in that relatively short period of distance. And what this saying is, be it this charge like the magnets or an actual negative charge or a positive charge, this Coulomb law, what this does is a measure of the strength. And it says that the attraction between two charges is proportional to the magnitude. Well, that makes sense if you think about it. Proportional meaning that if one variable goes up, the other one goes up the same amount, or it goes up. Could be a different amount, but it goes up. That's proportion, directly proportional. Okay, one goes up, the other goes up. Sort of like the more I study, better grades I get. Right? That's a direct relationship. And so if the charges go up, the strength of this force gets stronger. Makes sense, right? But it also says that it's inversely proportional to the distance squared. Inversely proportional, basically telling you that as one variable goes up, the other one goes down. What you don't want is study hard, grades get worse. Sometimes we feel that's what happens, but that's not what you want to happen. So inversely proportional means one variable goes up in value, the other one that's related to that variable drops, okay? And it drops by the square of the distance between those two charges. Now, let me put it to you in perspective. So we have this equation here, and for simplicity's sake, all I'm going to say is Q1, Q2 represents charges, and K is a constant. So what I can do is I'm going to combine those three variables and make it one constant. So my equation simplified is say force is equal to, I'm going to call everything X divided by R squared. Okay? So I simplify because I'm going to keep Q1 and Q2 constant, and K being a constant stays constant, so I can combine all that to make one big giant constant. Okay, we're not going to do anything to that. The only thing we're going to change is the R, which is the radius between the two charges. All right, so if I start with a radius, I'm going to say 1 unit distance. Don't have to be specific. And so the force is equal to X divided by 1 square, right? And so my force is equal to X, whatever the value of X was. Now, let's double that distance. We were at 1 unit, let's go 2 units. So that's number 1 example. Number 2 is now, it is X, force is equal to X divided by 2 square, which is X divided by 4, right? Which is basically 1/4 of X. And so by doubling the distance from 1 unit to twice the unit, that force now is 1/4 the strength. Okay, so that force between those two charges drastically dropped by 1/4. All right, so let's go the opposite direction. We started in example number 3. We started at 1 unit. Let's cut that unit in half. So we bring that unit from 1 to 0.5. And so now we have the force is equal to X divided by 0.5 squared. And if we look at that, we end up with a force that increased in magnitude by a factor of 4. Welcome to do the math now, you'll see that. Okay? That just by taking from 1 unit distance and decreasing it by half, that force went up by a factor of 4. And you know that by bringing 2 magnets together, opposite charge, and if you bring them together, you can feel that force repel. Or if they're the same, you can feel that force really attract the other direction as you get closer. Okay, so the takeaway from this equation, Coulomb's law is just saying is that the attraction between 2 charges is directly proportional to the magnitude of the charges, and it is inversely proportional to the distance squared. That's about it. Okay. This is also fine. This equation is also very similar to one of Newton's laws for bodies of outer space and how they interact with each other. All right, so what we have here is a table of questions, and they're asking you, is it a bond they're talking about? And if it is, what type of bond? Or are we talking about IMF? Okay. And if it is an IMF, then what type of IMF we're dealing with? All right. Now, to answer these questions, the key here is to read them carefully because, one, the way it's worded, you have to discern as to, are they talking about the molecule within the molecule, or are they talking about interactions of that molecules with other molecules of the same? Okay? And that's going to distinguish between the type of bond it is versus the type of IMF. Now, if we determine that they're talking about, the question is asking about IMF, then we have to determine, okay, what's its polarity? Is it a polar compound? Okay, and because that's going to tell us what IMF, either being London forces, dipole dipole, or hydrogen bridging, or ion dipole. Okay, so question 1: what holds the atoms together in one ammonia molecule? Okay, so they're talking about within that molecule because I want to know what is holding the atoms together in a molecule of ammonia, NH3. Well, obviously that is a covalent bond, okay? Specifically a polar covalent bond. All right, second question, what is holding the sodium ions in water? So point 1, we're dealing with ions, sodium ions, and then we're dealing with water. So we have an aqueous system here, right? and we have an ionic compound in an aqueous system. That should direct you to the ion dipole force. All right, so next question. What is holding 3 HCl molecules together? All right, so they're talking about holding 3 of them together. So obviously we're not talking about the bond of hydrogen between hydrogen and chloride, but we are talking about the interaction between molecules of HCl. So that's an IMF, okay? So being an IMF, we know that HCl is polar. That bond is polar. So therefore we can eliminate London dispersion forces and ion dipole forces because there's no ion mentioned here. So only choice you got left, be dipole dipole or hydrogen bridging. Well, we can eliminate hydrogen bridging because that only pertains to hydrogen bonded to nitrogen, oxygen, or fluoride. Here we have hydrogen bonded to chloride. Therefore, the only logical choice left is dipole dipole forces. Okay. What is holding the ions together in salt? No mention of water, so it's not an aqueous system. We're talking about what is holding the ions together in salt, sodium chloride, which is a metal and a nonmetal, which tells you that it is an ionic bond. Ionic bonds are holding these ions together. Next question is asking, what is holding 4 hydrogen H2O water molecules together? So again, no ions involved. We know that H2O is very polar. That's an automatic thing. Water is the most polar thing there is, okay? And so obviously no London dispersion forces. So that leaves us with dipole-dipole hydrogen bridging. The fact that we got hydrogen bonded to oxygen, automatically hydrogen bridging. Hydrogen bridging forces. All right, so what holds nitrogen gas molecules to each other? You're talking about to each other. That should tell you that we're talking about intermolecular forces. We know that nitrogen gas is diatomic. And being diatomic, it is nonpolar. Being nonpolar, the only thing you got is London dispersion forces. Okay, London forces. What is holding the oxygen together in an oxygen gas molecule? So we're talking within a molecule and not with other molecules of oxygen. And so again, it's simply a covalent bond, specifically a nonpolar covalent bond. That is what is holding the oxygens together in a single oxygen gas molecule. And then what is holding 2 ammonia molecules together? I'm hoping by now, hopefully we've done ammonia numerous times. The formula for ammonia is NH3, which tells you that it is a dipole-dipole. However, we got hydrogen bonded to nitrogen. So therefore, it has to be hydrogen bridging. Okay? Hydrogen bridging. Again, I repeat, we have nitrogen bonded to 3 hydrogens, 2 lone pairs. Okay, so that's why that's hydrogen bridging. All right, so basically to summarize all this in the flow chart, it's got kind of a little bit crooked. We have here, we have identified as a covalent bond compound. Now the question is it polar or nonpolar? If we identify nonpolar, then the only thing we have for it with respect to IMF is London dispersion forces. If it is a polar molecule, well then if they're talking about ions and say an aqueous systems, then we go directly to ion dipole interaction, okay, as far as intermolecular force. If it is hydrogen, which is bonded to either nitrogen, oxygen, or fluoride, then again, here it's automatically hydrogen bridging force. That means if it's not those two, then the only thing left is a dipole force, okay? As far as assigning what IMF to that molecule. All right, so given this information about the forces, now it will allow us to do some relative measurement and relative comparisons of what we call vapor pressure, boiling point, surface tension, and viscosity, okay? All right, so let's take a look at vapor pressure. The best way to think about vapor pressure, I think, is a soda pop container. And so we got the soda pop here. Okay, I'm not the best color. And then we have the liquid of soda pop. And actually got the cap on it. Okay, it's been capped up. Well, we know that there's gas molecules in these open space up here. If we were to put in a meter here on the open space, we will be able to measure pressure, because pressure is determined by the gas molecules in space, okay, in open space, as compared to the ones that are in liquid, right? Well, anyway, the more molecules we got in this open space of this bottle, that pressure is going to go up. It's just like you got a tire that's low on air. You got a quick trip, right? What do you put into the air? You put more air into it, right? You put more molecules in there. Guess what? The pressure goes up. And the same would be true of the soda bottle here. Keep it capped. I still got a meter here that's measuring the vapor, the pressure. If I were to take that soda bottle and shake it up, that pressure will go up, okay? Because we're getting more gas molecules into the air. Now, the thing to remember about these IMF interactions is this. If these IMF interactions are very strong and they're holding the molecules with each other strongly, you're not gonna have a lot of gas molecules going to the air. Why is that? Because the gas molecules in the liquid are being held to each other very tightly, okay? And we'll have more to say about that here in a second. So, vapor pressure, it's just the gas molecules that are in a closed container. We can measure that. Obviously, if we had no lid, it would, air molecules will go away. Eventually, your soda pop, you ever had that soda pop uncapped someplace, left it for a couple hours, you come and take a drink, it's pretty flat, right? It's because the carbonation is left. All right, so the question here about vapor pressure is as follows. Let me correct this here. Vapor pressure is the pressure exerted by gas molecules above a liquid in a closed container. Strong IMF would have a lower vapor pressure, okay? Think about that for a second. A strong IMF in the liquid phase will have a lower vapor pressure. Why is that? Because the molecules in the liquid phase will be held on to each other much greater than others. So be less molecules of gas will go into the air. So you can see here that A, okay, must have the weaker IMF. And why is that? Because there are more gas molecules in the vapor phase, okay? Because B, and thus the vapor pressure will be greater for A. B, on the other hand, the interaction of the molecules here in the liquid between each other is much stronger than A. Okay? And so less molecules are being pushed into the gas phase, and hence the vapor pressure is lower. Okay. Does that make sense? Because this is what all these physical properties are about. Think about what is happening to the molecules in the liquid phase. If they're being held on tightly or loosely, that's going to have a big effect on these physical properties that we're going to talk about. All right. Now, the boiling point. The boiling point is that temperature that a liquid will go into the gas phase at whatever ambient vapor pressure we are at, whatever pressure, atmospheric pressure we're at. Obviously, the boiling point of, say, you're up in the Rocky Mountains is a lot different than the boiling point here in Arizona, because we have a different atmospheric pressure, okay? So, but the same concept we just talked about with vapor pressure affects the boiling point. So the stronger the IMF, the higher the boiling point, okay? I'm going to repeat that. The stronger the higher IMF, the higher the boiling point, because those molecules are being held down more tightly than, say, a different molecule for somebody has hydrogen bridging, for example. That energy required is going to be a lot more than, say, for a molecule that's, say, dipole dipole. We'll do some examples here in a second. That is why, in that example I used earlier, where we had water versus fingernail polish remover, which is acetone, that is very volatile. And so water has a very strong IMF interaction, keeping the molecules out of the vapor phase as compared to acetone, which is much weaker, and therefore more molecules are going into the vapor phase as compared to water, okay? The same is true for melting point. Melting point is that temperature that a solid goes to liquid, okay? So strong IMF also means a higher melting point. All right, surface tension is basically a measure of how well these molecules hold on to each other. And, you know, I'm sure you've seen how if you put liquid on the surface, it beads up. Or it may not, it may flatten out. Yes, the surface energy is a factor, but the liquid itself, you know, if we look at a standard surface and we put the liquids on there, we'll see that some liquids tend to bead up. And again, A represents a liquid that beaded up because the interaction between the molecules in A is stronger than in B. Okay. And all right, now viscosity. Viscosity is a measure of resistance to flow. We all know, if not, we've probably seen people, you get a cup of honey, compare it to a cup of water. Put them a cup of each and then do the race. Empty the cups and see who wins. Obviously the water will, right? Because water is a lot less viscous than honey. Okay, so honey takes a little time, honey syrup, to flow out of that cup. Because those interactions between the molecules of honey/syrup is much stronger than that of water. And so it affects the viscosity. They hold down to each other much tighter. Now, how can we make the honey flow a little faster? What do? We heat it up. Doesn't that make sense? If you heat up that honey, that's going to cause the viscosity of the honey to get less and become more flowable. Because what we're doing is, by putting energy into the system, we are breaking up that interaction between the molecules. Okay? So we know that oil flows slowly because high viscosity as compared to, let's say, the alcohol vodka, which has very rapid because of low viscosity. So A strong IMF would give you a higher viscosity, again, because the molecules are being held on to each other much, much greater. Okay. Well, here we're going to do a compare and contrast. And like I stated before, we can't do absolute comparisons, but we can do relative comparisons. Before we do this, we got to know what? We got to know what the formula is. From the formula, we can determine the polarity of the molecule. So let's write ammonia. Ammonia is something we talked at length about, okay? And we know that this is a polar covalent. Oh, misspell it. Covalent compound. Okay. And fluorine is diatomic, and so it is nonpolar. Okay. Since ammonia is polar, and it's a polar covalent compound, plus it is hydrogen bonded to nitrogen, guess what the IMF would be? That would be hydrogen bridging force. Okay. Since fluorine is nonpolar, then the only force it has is London dispersion forces. And so we first have to figure out the formula, which we did, which then tells us the polarity, whether it's a polar molecule, okay, or not. And we know that ammonia is very polar, and plus the hydrogen bridging force is involved, and London forces for fluorine. So with that information, we know that HBF is a stronger force, okay, compared to London force, which is the weakest. And so you may have some questions that says, well, which is the stronger IMF? Well, obviously HBF, hydrogen bridging force, which ammonia has, okay? Which has a lower boiling point? Well, the one that has a lower boiling point, that would be the one with the weakest IMF, and that would be fluorine, because it has the London forces only. Which is polar? We know based on the exercise we did earlier that ammonia is polar. Fluorine is diatomic. Being diatomic, it is nonpolar. Okay. And then who has the higher vapor pressure? Since ammonia has the stronger IMF, that would be the lower vapor pressure, which means that fluorine, which has the weaker IMF, has the higher vapor pressure. And if we could compare and contrast these two as liquids, the question is, which is the least viscous, okay? And again, that would be fluorine. And ammonia will have the more tension, surface tension. Now, the questions could have been reversed. Number one could have been said, which has the weakest IMF, okay? Number two could have said, which has the higher boiling point? Okay, so these type of questions can easily be moved around, changed, be given to you in a different manner. Okay, to rehash this, we've got about a minute left. One, you must know the formula of the compound you're given. From that formula, you determine the polarity of that compound, and from that polarity, you determine what force to assign it. Okay? All right, so I tell you what I'm going to do. I'm going to stop it here, and I will continue with this. We don't have much left, but I will continue this chapter on Tuesday. Okay? Thursday, again, it's open study day. I'm here. Come with any questions you may have. We can, I'll be here the whole time, our regular time. So if you have any questions, come bring them to class.